Hi everyone. If you wondered how you get the highest grades in physics or in science generally, the specification is a really good place to start. Specification and applying it to exam questions. So don't trust YouTube videos, don't trust revision guides, do your own research, look at the specification. In this video, I've got a few different parts that I think are generally quite poorly understood to do with forces in motion, EM spectrum, space, electromagnetism, the whole thing. So this is just from my experience as a teacher and an examiner. If you watched my last video about different parts of the specification that you need to know to help you get a 9, you'll notice that alternating potential difference came up on paper 1 of the 2025 paper. So if you didn't talk about potential difference, you talked about current, you're not going to get any marks. So make sure you watch this video. There's some similar sort of insights into the specification you might not know or might not be explained that well in your revision guide. So I hope you enjoy. We're going to start off with inertia, which is the topic of forces and motion. So inertia, you need to know if you're studying higher tier combined science or separate science, and is defined as the tendency of an object to continue in its state of rest or uniform motion. That means at a constant speed. Just like this rock here is very hard to move, we'd say it has a high level of inertia. You also need to know what inertial mass is, which is a very similar idea. Inertial mass is a measure of how difficult it is to change the velocity of an object. So if you want to change its velocity, if it's got a high inertia, a high inertial mass, it makes it more difficult to do. We can define inertial mass as the ratio of force over acceleration. So when we say force over acceleration, that comes from our definition from Newton's second law, F equals ma, which if we divide by acceleration, then we get the inertial mass. So it's basically just a rewording of Newton's second law. Another thing in the forces and motion topic is recalling typical values of lots of different things, which is part of the specification. I'm quoting it word for word here. So it says students should be able to recall typical values of speed for a person running, walking, cycling, as well as typical values of speed for different transport systems. So we need to know these. It could ask you to calculate something and say, does this sound reasonable for someone who's walking or running, etc. So someone walking is roughly 1.5 meters per second. Running is about 3 meters per second. Obviously, it depends on how fast you're running. Cycling is more like 6 meters per second. In a car, obviously it depends on how fast you're going, but usually between 10 and 30 meters per second. That's on a sort of dual carriageway or motorway. A train will be much faster at 50 meters per second, and a plane even faster still at 250 meters per second. So I would memorize those rough values just so you've got an idea. It's probably only going to be 1 mark in an exam, but we're aiming for full marks here, so why not get every mark we can? We also need to be able to estimate the forces involved in the deceleration of different vehicles. So when a car slows down, for example, roughly what deceleration is it going to be experiencing? So what we're talking about with an acceleration is a car stopping from, let's say, 20 meters per second. If it's going to stop from that time, it's going to take a few seconds to do so. So let's say 5 seconds to do so. So that's going to be, roughly speaking, 20 divided by 5. We're talking about 4 meters per second here. Now you might notice in all of these different approximate speeds, they've got a little squiggle sign. If you don't know what that means an approximate answer. So it doesn't mean it's equal to exactly 1.5 meters per second, just means it's very similar to. Let's talk, and while we're talking about motion, let's talk about stopping distance. So in stopping distance, you do need to be able to use a little bit of biology to be able to define reaction time and thinking distance when we're talking about stopping distance. So in a reaction time, for human beings, it's always less than a second, roughly 0.2 to 0.9 seconds. You do need to know a brief sort of rundown of the practical in biology for how to measure it. So it's this kind of thing here where you've got the ruler and you're dropping it. A method on how you do that would be to say something like you drop the ruler at a random time without counting down so the person can't predict it. You then catch it. The distance up the ruler which you catch it is proportional to the person's reaction time. A greater distance means a greater reaction time. You could change a bunch of different things. You could change distractions. You could give the person alcohol. You could do loads of different things to vary their reaction time. But you do need to be familiar with that experiment. While we're on about stopping distance, you need to be able to interpret a graph relating to stopping distance for different vehicles. This is for physics only for higher tier. Now, a graph to do with stopping distance might look a bit like this, and I've also put in braking and thinking distance because there's nothing on the spec that says it could come up, but one of those things which they love putting graphs in exam questions. There's no reason why it couldn't. So in red, I've got the thinking distance down here. So as speed increases, we can see the distance, the total thinking distance increases is a linear correlation, meaning that distance is directly proportional to speed. The reason for that is because distance equals speed times time. The green line, however, the braking distance, is not proportional. The relationship it is here is that distance is proportional to the speed squared. So as the speed doubles, the distance would quadruple. Now I'll show you why this is the case in a second, but we've got this equation up here, v squared equals u squared plus 2as to help us out. So as the speed of the vehicle increases, we've talked about thinking distance already, it increases linearly, but the braking distance increases as what we call a square relationship. So if I was to double the speed, the braking distance goes up by a factor of 4. If I was to triple the speed, the braking distance goes up by a factor of 9. Notice that 4 is 2 squared, 9 is 3 squared, and so on. The reason for this is due to the v squared equals u squared plus 2as equation. I've just rearranged it there to make it a bit simpler. If we just pick out v squared and, v squared and s, v squared is proportional to s. You could also use the kinetic energy equation and work done to prove this as well. Vector diagrams are something that you need to know if you're doing higher tier for separate or combined science. They're for you to use when you've got forces that are acting not in the same plane, i.e. not left and right, up and down. It might be one left and one up, and you've got to figure out what the resultant force is. You need to be able to draw a scale diagram. They're always going to be about 3 or 4 marks, and you need to be able to do them. They have come up a couple of times previously. So if I've got these two forces here, the first step is to draw a scale diagram tip to tail. So I'd make, say, 140 newtons, let's say 1.4 centimeters, 220 could be 2.2, you could double that, whatever scale you use. You don't have to use 1 centimeter equals 100 newtons, just stick to your scale. Once we've drawn those arrows in, we then draw a resultant force arrow that goes from the corner where you started to the end of the second arrow. So in here I've drawn it in green. Then you measure with a ruler, so in this case this happens to be 2.6 centimeters, that will be 260 newtons. So then we can measure the direction. Sometimes the opposite direction, you use a protractor. Make sure you have a protractor in your physics exam to measure that. Sometimes you get force arrows that are not perpendicular. So there, in that case, you might have to draw a bit of a different shape to be able to work it out tip to tail, but it's the same principle really. You also need to be able to do the opposite. You need to be able to resolve a single force into two components that are right angles to each other. So in this case, I'm going to go work backwards. Let's say I've got 10 newtons at a certain angle. I need to be able to resolve it into horizontal and vertical directions. You do that by drawing a diagonal line to scale if it's not in the question. Then you sort of complete the rectangle by drawing little grid lines, and then you draw the arrows on vertically and horizontally and then measure them. Whatever scale you've used, you need to be able to use that again. So in this case, let's say I've got 8.2 centimeters and 4.2 centimeters. We just convert that straight back to newtons. Next thing we need to know is about speed of sound. So speed of sound, you do need to be able to describe a method to measure the speed of sound in air. Now this method is very sort of, very slightly basic. It will work to an extent. But basically if you have someone like clapping something very loud, or like a starter pistol, something like that that's very loud, if you measure out a really large distance, about 100 meters or more, so the time taken is long enough to be measurable and doesn't get affected by reaction time, one person bangs the cymbals together, another person uses a stopwatch to record. They time between them seeing the cymbals crash together and them hearing the sound, and then they divide the distance between them and the big noise by the time they've just measured, and you find the speed of sound. You do also need to know that a typical value for the speed of sound in air is about 330 meters per second. It will go up in a solid, it will go down, go also up in a liquid. It travels faster, the particles are closer together, but 330 is what it is in air. Refraction is something else we need to be able to describe really carefully. This is quite a common thing, common question to come up. You could be asked to draw a ray diagram like this. So when light goes from air to glass, it goes towards the normal. But more commonly, and generally gets answered way worse, is to use wavefronts. So students should be able to use wavefront diagrams to explain refraction. So a wavefront diagram looks something like this. Instead of like a wave just being as a line, you have essentially each line is like a wavefront, like a ripple in water. Each line is a peak of a wave, so the distance between them is the wavelength. So how you describe something like this is why a wave refracts. You'd say the right-hand side of the wave hits the water first, is a more dense medium, so it slows down. The left-hand side of the wave, so the bit that hits it second, just carries on at its normal speed. Then it hits it, but in that time, the wave has all turned because one side is traveling quicker than another. So we'd say the left-hand side carries on at the same speed, the wave then bends right or towards the normal, depending on which direction you've got in a diagram. Let's talk about radio waves. This comes up so much, combined science, separate science. Being able to describe how radio waves are produced and how they're detected. So on higher tier, we need to know radio waves can be produced by oscillations in electrical circuits. Electrical circuits have electrons in them. When they oscillate, or they go up and down, up and down, up and down, they produce radio waves. When that happens, they can be detected by a detector. So in this case here, we've got a transmitter emitting the radio waves, And we've got a receiver, which is made of metal as well. When the electromagnetic waves are absorbed by the electrons in the receiver, they also oscillate. That's also known as alternating current. So you can get really cheap, easy marks if you memorize this. This is literally just the specification. When radio waves are absorbed, they may create an alternating current. So in the aerial, which is metal, it says with the same frequency as the radio wave itself. So if the radio wave is 10 hertz, the electrons are going to go up 10 times a second, or at 10 hertz as well. Let's talk about electromagnetic radiation. It's a really niche part of the spec here for AQA. Students should be able to give brief explanations of why each type of the electromagnetic wave is suitable for practical application. So here are the uses from the spec. We should be familiar with all of them already. This isn't sort of the grade 9 stuff, but to be able to link their wavelength or frequency to their uses is really important. So the long wavelength for radio and microwaves are used for communications. That's because they can easily pass between hills, between buildings, sort of over mountains. They do something called diffract, which you don't need to know for AQA, but they spread out really easily because they've got a long wavelength. X-rays and gamma rays have a really small wavelength, which is really important. The reason they are used for medical imaging is because they can penetrate inside the body, and X-rays don't penetrate through bone, which is really important. And they also have, for gamma rays, they're used to treat cancer because they have a high frequency. High frequency means they have a high energy, so they have enough energy, ionizing enough to destroy cancer cells, which is what that use is. Also related to electromagnetic radiation is how they're produced. So they're produced by changes in atom, and in particular changes in nuclei, resulting in EM waves being generated or absorbed over a really wide frequency range. That means, well, I'll show you the diagram in a second. I'll be honest, this is proper A-level physics. This statement is the only thing you could be asked about. But essentially what happens is electrons, if they absorb some electromagnetic radiation, they can jump up one shell. When it says range of frequencies, it means the higher the frequency, the higher they can jump. The lower the frequency they absorb, the lower they can jump. The opposite is true for when EM radiation is emitted. When the electron goes back down, it emits electromagnetic radiation. Again, it can be a range of frequencies. It could be like gamma rays, it could be an X-ray, whatever. It just depends on how big that energy jump is. Blackbody radiation is something that I guarantee people won't have revised that much. It's a really long bit in the spec. Very few exam questions have come up about it, but I'm going to talk you through it and then we can have a look at a quick exam question on how to answer questions to do with blackbody radiation. So don't be scared of it. Blackbody radiation sounds horrific. It's honestly not that bad. The idea is that all objects, no matter what temperature, will emit and absorb infrared radiation unless it's absolute zero. So that's as cold as it could be. The hotter the body, the more infrared radiation it emits. A perfect blackbody is an object that absorbs 100% of the radiation that hits it or is incident on it, and it doesn't reflect or transmit any radiation. All it does is it absorbs all of it, but also it's the best possible emitter, or the perfect emitter. So I know it's hard to imagine, it's a hypothetical thing, it's not a real object, but it absorbs all the radiation, but then it's also kind of emits 100% of its radiation as well. So a new way of thinking about it is like this. Imagine a really small hole in a sort of very dark object. Light goes in, it bounces around so many times, it gets absorbed a little bit each time that it doesn't come back out. That's a perfect absorber. Because the object is black, any light it absorbs will heat it up a bit and it sort of emits that as heat outwards. Okay, so that's not a perfect analogy, but it's not too far away from what it actually is. And a good way of thinking about it, you've got lots of different paints and things like that are very dark. This is called Vanta Black. It absorbs 100% of the radiation incident on it, so that it kind of just looks weird. It's not reflecting enough light because it's such a good absorber. Told you it was a long spec statement for black bodies. Nothing in here is that terrible, I promise you, okay, but it's worth knowing. It's all about how the objects reach equilibrium depending on how much radiation they emit or absorb. So it says that all bodies or objects emit radiation. The intensity and wavelength depends on the temperature of the body. Now, we're going to have a look at that a little bit later. But generally speaking, if you absorb more infrared radiation than you emit, then you're going to have a temperature increase. If you emit more than you absorb, you can have a temperature decrease. That's kind of just common sense. In planet Earth, when we look at this diagram here, you'd be familiar with this from chemistry and biology as well. Greenhouse gases. When EM radiation goes through the gases around the atmosphere, at most wavelengths they pass through, the Earth absorbs a little bit, heats up, and then it re-radiates or reflects some of it as infrared radiation. Now some of that is then re-reflected back down by the greenhouse gases and some of it transmits into space. That's essentially what it's talking about here with this point down here where it talks about how the temperature of the Earth is affected by rates of absorption and emission. So lots and lots of words here. Promise you it's not that bad. I've just been through essentially the basics of it. So an exam question to do with it, this came up in, it's actually one of the specimen papers they released when they made the specification. It'll be one of those things where people will be really surprised and like, oh my God, if it came up in the real thing, but let's go through a question about it. So blackbody radiation, we've got a box very similar to what we've looked at previously. It says, why does the small hole look black? So we had something like light is reflected many times. Each reflection, a bit of energy or light is absorbed, so very little leaves, so therefore it looks black. Next question, it says, all objects absorb and emit radiation. What is meant when an object is described as a perfect blackbody? You essentially just quote that line in the specification. If in doubt, look at the specification, what words does it use? You'd say it absorbs all the possible radiation incident on it and is the best possible emitter. We could say a perfect emitter of radiation. Next question, we've got a quite interesting looking graph here, which shows how the intensity of different wavelengths from a hot object varies with temperature. You might find a graph similar to this in revision guides. You do not need to memorize it, but if it comes up in an exam question, it helps that you're familiar with it. So a question might ask, what can be concluded from this graph about how the distribution of the intensity of radiation from an object changes as the temperature increases? Essentially, at different temperatures, how does the intensity vary? Classic sort of graph question. So at different temperatures, we can see the peaks shift a little bit. So the maximum peaks will be lower, and also the intensity at hotter temperatures is always higher. So let's just put this in a couple of bullet points. We could say as temperature increases, the intensity increases for every single wavelength. They're all higher from this graph. The shorter the wavelength, the more rapid the increase in intensity. So it's a steeper curve on this 1400 degree graph. And then the peak intensity occurs at a shorter wavelength. So you see the peak for the 1400 degree one is a bit further along than the other ones. This question also asks you to estimate for the sun. It has a maximum intensity of radiation about 5 times 10 to the power minus 7 meters. What's its temperature? Well, we can see here the 5 times 10 to the minus 7 barely touches that line here, 1400. It doesn't peak for any of these lines. So it's actually asking you to estimate. We don't have the information here to know exactly, but it has to be significantly higher than 1400. So you could say 1600, you could say 2000. They actually allow any answer in here between 1600 and 10,000 degrees. Just by looking at the graph and figuring out it must be a fair bit higher for it to peak in this region where 5 times 10 to the power minus 7 is the wavelength. Let's look at our last question to do with this, and this looks like a horrific question, but if you look at the numbers, W is watts, T is tera, so this just shows how much power there is overall. It says, explain how the temperature of the Earth and its atmosphere has changed over the last 200 years. Use the information in figure 3. So if you look at the radiation that goes into the Earth, it's the same 170,000 terawatts. We've got 120,000 emitted 200 years ago. Now we've got a bit less emitted, and we've got a certain amount emitted into space. So where's that missing energy gone? Hopefully we could figure out it's gone into the Earth, it's been absorbed, so it's therefore changed the temperature, it's increased it. So we'd say something like 200 years ago, the radiation from space was equal to that emitted. So we've got 170,000 equals 120 plus 50,000. Now, on the right-hand side, we've got less radiation is emitted than has been absorbed, so therefore the temperature increased. So don't overthink it. It's usually, they can't ask you anything that's not on the specification. So just think about what can I apply to this question, and that's enough for 3 marks for this exam question, and finishes the whole thing. Right, we're going to finish off on a little bit of space, which is a separate only topic. So when we talk about space, we need to be able to talk about how new elements are produced. We should all be familiar with the star life cycle if you're doing separate science. You need to be able to say in which part of the cycle do we get different elements being produced. So helium gets produced in main sequence, which is when you get hydrogen. So I've misspelled that there. Hydrogen becomes helium. We get fusion of heavier elements like carbon and oxygen happens in red giant or red supergiant stars. In red supergiant, it goes all the way up to iron. That's the heaviest element that gets produced. All elements heavier than iron happen in a supernova. So things like all the metals, basically transition metals, gold, tin, silver, uranium, are in supernova. They get scattered all over the solar system and over the universe, basically. So a common question is to get something like, how do we know our solar system is formed from a supernova? Well, it's because we have these heavy metals, heavy elements. We have loads of gold, we have quite a lot of uranium, therefore must have come from a supernova somewhere, an explosion of a star. The very last statement on the specification is an interesting one. It says there's still much about the universe that is not understood. For example, dark mass, which we usually know as dark matter, and dark energy. So dark matter is this thing we don't know hardly anything about, but it kind of pulls galaxies together. There's not enough mass that we can see that's responsible for that. Dark energy is something completely different, but is used to describe the rate of the universe expanding is accelerating. Why is that? We don't really know, so we call it dark energy. The last thing we're going to talk about is that on paper 2 you can get some paper 1 content to do with energy and things like that. So all these statements here, I'm not going to go through them all in detail, are also included in the paper 2 for GCSE Physics. So you need to be able to talk about work done and the equation. You need to be able to talk about energy transfer. You need to be able to talk about elastic potential energy, frictional forces, all that kind of stuff, and to be able to convert between something called Newton meters and joules, which I'll talk about now. So none of this should be new, but just bear in mind you could be asked for paper 1 equations can come up in paper 2. When we talk about Newton meters and joules, work done equals force times distance. That means 1 joule for work done is equal to 1 Newton times meters. That's just another way of saying that. It's just like saying Newton meters. So 1 joule is 1 Newton meter. It's your alternative unit for energy, basically. Right, electromagnetism I'm not going to have time for in this video because it'll be far too long. But I have made a really long explainer video about all the stuff you need to know about things like the generator effect, things like loudspeakers, microphones. They're usually at the end of the paper for AQA, and they are usually the worst answered questions because you're usually tired at the end of the paper and they're very poorly understood. So I've linked in the top here. Please watch these videos and actually understand and word perfectly take notes, because if there are 4 or 5 or in a 6 marker, you're going to be kicking yourself if you haven't revised them properly and word perfectly. Could be a thing that stops you getting the highest grade. There we go. So I hope you found that really useful. Please leave a like if you did, and more importantly, actually revise this stuff, because if it comes up, then you're going to be thanking me, and also helps you understand lots of other parts of the physics topic as well. But I'll say bye for now, and good luck in paper 2.